Hello and what's up to you all matriculants? Welcome to your favorite show. It is Physical Science with me, AB. I hope you enjoyed your Easter weekend. We're going to have fun today, learning more and learning extra matrics. We don't have any more time for you guys. It's time to work more. Tracy, how are you?
Fine, and you, AB?
I'm also good. I'm feeling good, hey?
Good.
How was
yes.
your Easter weekend?
Busy. I was working.
That's what we
need.
need.
Matrix for them.
There's no time to play, Tracy, hey?
No.
Well, I'll tell you what, during the Easter weekend, you know that as Mindset, we're promoting that the Mindset should follow us. Have you liked our page?
Long time ago.
Oh, awesome.
I was one of the first.
You're one of the first ones.
Yeah, I've been here forever.
If it was for me, I would give you this calculator.
I don't think I qualify.
If it was for me. But otherwise, during this weekend, we've reached our target, which was 75,000 likes.
Wow.
So now we're on 75,399.
Wow.
So we're getting there, hey?
That's incredible, though.
But tell me, how was your weekend?
Busy.
As
You
always.
asked me this question already. He's getting old.
You know why I'm asking?
Why?
Because I spoke about the Easter weekend. And as Mindset, as we've reached our target, we have something special just for our teachers.
What have you got?
For us as presenters.
What?
I'll tell you, but tell me, what are we doing today?
You know, that's just rude. I'm just saying. I think he's just being mean. Today, we're going to carry on with what John was doing with you guys last week. Last week, John started the WorkEnergy Theorem, which we know causes a bit of stick, and we didn't quite finish all the questions. So today, we're going to look at work again. We're going to do a little bit of revision, WorkEnergy and Theory, and then we're going to add power to it.
Nice one. Work and power. I like that. Well, I wasn't playing,
Yes.
but unlike the rabbit that you have at home, I have something special for you. This is just for you. It's not a real one, hey? But you can eat this one, hey?
Oh, I like that.
Nice one. Cool.
My first Easter egg.
Wow, nice.
That's
We
a bit
always like
sad,
to make
hey?
things special. But Mindsetters, remember, you have your notes. You can view your notes on the link that is provided on Facebook just for you guys. We have the challenge question that will be posted also on Facebook. But remember, follow us on Twitter at LearnExtra. The notes link and the schedule is on learn.mindset.co.za. Tracy?
My turn.
Let's
Cool.
work now.
Okay. So I'll make sure my bunny doesn't eat my bunny, or my kitten. Just so you know, in case anyone's wondering, these marks.
I see.
I have a kitten at home who thinks I'm his climbing gym, but he's so cute. I can't resist.
He was working and he had a lot of power.
He is. There we go. Well done. Alrighty. Let's just get on to the science part, shall we? Okay. Now we've messed up. Haven't even started yet. It's been a while. Can you tell?
We're
Anyway.
still on holiday.
Yeah, a little bit. I need another holiday. Okay, so guys, we're going to revise the WorkEnergy Theorem and we're going to discuss the concept of power, both of which are going to be asked. Okay? Now, first of all, we need to give you the challenge question for today. Okay? So this one's not a multiple choice question, and what I'm wanting, well, we'll get through what I'm wanting in a second. A force F acts on an object X, whatever that object is, for a time t, and moves it through a distance of x. The same force acts on a different object y for a time 2t, and it moves it through the same distance x. How does the work and power of each object compare? So what I'm asking you here is to compare the power of x to the power of y and the work done by x to the work done on y. Okay, are they the same? Are they different? Are they bigger? Which one's bigger? If one is bigger, of both of them. Okay, so we want work and power. And what makes this a little bit more tricky is I haven't given you any values. Okay, so I am going to give you a little bit of hint just to help you out there a little bit. I'm not quite that mean. It's probably a good idea to draw some sort of diagram just to get it clear in your mind as to what's going on, okay? So object X and Y have the same force, act over the same distance, but at different times, okay? All right, good. So going back to theory, now you learned this last week, but we're just going to revise it. Revise it. Okay, as my children would say, not my real children, my learners, they are my babies. I have not had enough coffee. Moving on. So, the WorkEnergy Theorem says to us that the change in kinetic energy, maybe a pen color would, there we go, let's use that one. the change in kinetic energy of a system is equal to or equivalent to the sum of the work done by all types of external forces acting on the system. What we're saying to you is if work is done by the system, there has to be a change in kinetic energy of the object. Okay? Now, by all types of external forces, so that includes friction, gravity, air resistance, all of those sort of things, okay? But when there's net work done, kinetic energy must change, okay? How do I know there's got to be kinetic energy change? Because there's got to be some sort of acceleration, okay? And this should be kinetic energy final minus kinetic energy initial. It's always final minus initial. You would have learned last week, that work can be negative. Please be careful with this, please, grade 12s. This is one of those strange little concepts in that we tell you that with the vectors, vector has to have size and direction. So when you get a negative vector, like for a negative velocity or negative acceleration, it tells you that that velocity acceleration is acting in the opposite direction. That's what the negative means. Work is a scalar. It has no direction, okay? But because of the relationship between work and energy in a system, work can be negative, okay? That negative is not a direction. It's simply referring to the object's energy, whether it is gaining energy from the system around it and from the forces around it, or it's losing energy because of friction. So for example, if our net work is negative, and that's generally because work is being done by friction, okay, friction's work is generally negative because what's happening is the system isn't losing energy. Remember, energy is always conserved. We have mechanical energy, which is potential plus kinetic. That is always conserved, okay? But, so not always conserved, I lied to you, but energy is always conserved. Now, there's lots of different types of energy. Sound, light, heat, chemical, potential, kinetic, elastic. There's lots of types. Now, in the system, we're only considering with this network what happens to the kinetic. So if this network ends up being negative, what it means is we're losing, and I use that term very, very loosely, losing kinetic energy, but it's becoming something else. So instead of being moving energy, the energy now has become sound or heat, particularly with friction. So when you hear a rough box on a surface, that's friction. You hear the noise and it gets hot. Okay, so that's where we're losing the energy. It's just turning into another form. So energy as a whole is always, always, always conserved. Mechanical doesn't have to be, okay, because there's external forces. So work is transferred is the transfer of energy from one form into another. Okay, that's what I've been talking about. And then we get to power. Now, power is defined as the rate at which work is done. We often talk about power in a slightly incorrect way. So we will talk about a weightlifter being powerful, having lots of power because they can pick up really big weights, okay? But that might not mean they're powerful because it depends on how long it takes them to pick up those weights, okay? So it's a bit about time as well. So our very basic definition is power is work divided by time. Work divided by the change in time. Nice and easy. That work over here can also be work net, okay? So it depends on what we're looking at. So it can be network as well. But sometimes our network ends up being zero because there's no change in kinetic energy, okay? So our object or our substance, whatever it is now moving at constant velocity. For example, when we have a hydroelectric power station and they pump water up from the bottom of the dam, they pump it up to the top dam so that they can go down past the turbines again. They can't have this water just accelerating the whole time because that just doesn't make any sense and becomes uncontrollable. So they pump the water up from the bottom dam to the top dam at a constant velocity. The motor that does that pumping is doing some sort of work, okay? So the motor has an average power, okay? Between the time it starts pumping to the time it stops, there's an average. That average can be calculated using the force that's being applied times the average constant speed. Very important with this equation, because I see this all the time, grade 12s. This equation can only be applied if the object is not accelerating. Must be at constant speed. Okay, and then you must know what the applied force is. This one comes up every now and then, so just be careful with that, okay? So, let's get on to work energy theorem, or our favorite thing to do. And we'll probably only get through the first part of this question, then we'll take a little break so our minds can think about it, and then we'll get on to the second part, because that's a little more difficult. A 5 kilogram trolley, so we've got a 5 kilogram trolley, let's use a different color so we can see it, moves along a horizontal frictionless surface at a constant velocity, so we've got a horizontal surface of constant velocity of 2.5 meters per second, and until it comes to a ramp that is inclined at an angle of 12 degrees. And now we start to sweat, because now we're seeing angles. The surface of the ramp is rough, so that means we've got friction. The trolley comes to rest after moving a distance of 1.2 meters up the ramp. Wow. You know what? Let's draw a diagram. Best thing we can do here is draw a diagram before we do anything else. So I'm going to calculate the work done by gravity, but let's draw a diagram. So they say to me, we have our trolley. Now, we all remember, because we've been around for a while, that I can't draw, okay? So we'll just go with it. So we have our horizontal surface. Here comes my 5 kilogram trolley over here. Hits a ramp of 12 degrees. Yes, I know I've made it much bigger than 12 degrees, but it's okay. That's 12 degrees. It gets to this point going at 2.5 meters per second. Then it travels, and I'm going to do this deliberately, 1.2 meters this direction before it stops. When it stops, that means the velocity over here is 0. We're going, cool, that sounds, we can do this. Now they say calculate the work done by gravity on the trolley. Now we start to remember some grade 11 stuff. What is happening here with the trolley actually is irrelevant. It's what's happening to the trolley on the slope that's important, okay? When the trolley's on the slope, remember that gravity, and I'm going to pretend the trolley is over here. Gravity acts vertically down. That's Fg. What I need to know is, in order for me to work out, so if I go, well, work done by gravity is the force of gravity times delta x cos theta, okay? Now, there's lots of ways you can do this, but I'm going to say, let's just be clever about this, okay? I want to use the 1.2 meters because that's the distance I have, which means I actually can't use Fg because Fg and 1.2 are not in the same plane, okay? So what I do want to do is I want to find Fg parallel, because if I can find the parallel component of Fg, then I'm sorted. I'm A for away, okay? So Fg, now all of you will have been taught how to draw these diagrams differently. It doesn't matter. I like to do my Fg over here because it's just easier for me. So there's Fg parallel. This angle is my 12 degrees from my slope, and it's all starting to blur. So I'm going to use sine. So the first thing I'm going to do, Fg parallel is equal to Fg, that's my force, times sine theta, okay? Now what makes this horrible is that there's lots of thetas everywhere, okay? But just go with me. So Fg, which is going to be the 5 kilograms times 9.8, we're going to times it by sine 12 degrees, and I went and worked this out beforehand just to make life a little bit easier, and we get 10.18. Hopefully all of you have followed me so far, okay? So I need to change this equation quickly because I'm not actually using FG. I'm using FG parallel. Wrong one. There we go. So I'm using FG parallel delta x because I can use the 1, 2 and cos theta now. Okay. FG parallel is 10,18. We're all happy with that. The distance is 1, 2. Now comes the fun part. What is the theta for here? Guys, now you've got to think very carefully. Okay? The trolley is moving up the slope. The parallel force due to gravity is moving down the slope. Gravity is not helping this trolley at all. Gravity is what's going to help stop it, okay? Besides the kinetic friction. Gravity is going to help stop it. So, that means cos here, this has to be 180. And cos 180 degrees is minus 1. So when I put this into my calculator, I get minus 12,23 joules. Before you say, well, that's definitely the answer, you now have to look at your answer and go, does it make sense that this is negative? Yes, because gravity is making the system, gravity is making my object stop. Okay, so it's opposing its motion, so it's taking the kinetic energy away from it. So it's negative, okay? So stick with that in your brain because we're going to take a small break because when they come back all fresh and together with me, okay, is we're going to then calculate the frictional force on the slope.
Okay, and this will come in very handy. I'll tell you guys after the break about this awesome giveaway of a Casio calculator. See you after this break. Welcome back, awesome Mindsetters. Now we have this exciting giveaway of a Casio calculator. All you need to do is to view the notes and then do the test yourself questions. Submit your answers on the form that is provided. There's a link on facebook.com/learnextra. Whoever gets most answers or all the answers correct within this time of the show and tomorrow until 4 p.m. So make sure that you send in your right answers and you could win this awesome calculator that has about 254 functions.
Oh, is that all?
Yes, 254.
Why doesn't it have 55?
You can create the 55th one.
Yeah, no, I'm sure I could if I tried. No, 250. I think that's pretty useful, huh? I actually really like the Casio out of all
and
the
later on, you're going to show us some trick for the matrix.
Oh, yes. My favorite thing.
It's a trick
that
for
drives
matrix.
me mad.
Oh.
Because they don't know how to do it.
Okay.
You see, because I tell my kids, go do this, and they go, it's like this blank look. And then I go, okay, never mind.
Okay.
You know.
You'll show them.
I'll show them.
Awesome.
And then you can just slyly do it. Shh, don't tell anyone. Okay, so moving on. In fact, I learned something watching John today with the fractions.
Okay.
So I don't like that function, but it's a good one. I just don't like it. It's an old school thing.
I hope John is not watching.
No, it's just me. It's one of those things. Let's move on. Anyway, so next part of our question says, calculate the magnitude of the force of the kinetic friction. Guys, it doesn't matter whether it's kinetic friction or static friction that they ask here. They wanted friction. The only reason why it's said to be kinetic friction because the object's moving. Okay. So now we go to the fun part and we say, okay, where do we start? We know we're looking at work. So we're going, okay, I've got the work done by gravity. Great. But now I want friction. Okay. So somehow, if I can work out the work done by friction, then I can work out friction. But how do I work out the work done by friction? Because I don't know the frictional force and I don't know X. Well, I do know X and I know, So we're going to go right back to the WorkEnergy Theorem because that's exactly what you have to use, okay? Which says to us that net work is equal to change in kinetic energy, okay? We do net work by the net force, okay? So just stay with me. what you have to recognize, this is very important here, okay, is that your gravitational force acts parallel to the slope and acts down. Friction always opposes motion. Always, always, always. Which means the trolley's moving up the slope, which means friction and gravity's acting down. So friction acts in the opposite direction to the applied force. Friction's that direction. Friction's stopping it from moving. Okay? We all with me, I hope? And I'm suddenly... you know what? Sometimes I have these moments where, you know what, I really should just rethink what I did, and friction goes down. Okay? Because friction can't go up, because why can't it go up? I'm just testing you're all awake, and right now, maybe he's just thinking this is hysterical. Friction can't go up, because the trolley's going up. So friction has to move down. So friction moves in the same direction as work done by gravity. So, that means, now we get here and we say, fine, okay, W net, now watch where I'm going, is equal to my change in kinetic energy. Change in kinetic energy I can work out because I know that it started at a velocity of 2.5, ended at 0, so that's easy enough. W net means that I'm going to have to use F net delta x cos theta. Okay, just wait, let me write it like this rather. So I'm going to go EK final minus EK initial. It's always fine, it's minus initial. Now in my head, I go F net. Well, actually, my F net is going to be my gravitational component plus friction. Okay? You can do it as FF, it's fine. I want you to see the difference. That's my friction. Delta x cos theta. Now, and all we're doing is developing the equation right now. So now we're going to go half, well, final, I don't even have to work it out because my final kinetic energy is 0. It stops, okay, minus my initial, okay. Now we go, hang on, wait, I know FG parallel, we worked it out. I know delta x, it was 1, 2. We're just going to have to think about theta. And that's 0. I know the mass, it's 5. And I know v, it was 2, 5. It's a substitution problem now. These 3 lines, that's the signs. Okay, after this, now it's a maths problem. So now we go, okay, FG parallel, we worked it out and we said it was 10,18. Okay, we don't know friction. So that's what we're going to work out. Delta x is 1, 2. Oh boy. Now, what is the angle for theta? Once again, we have got to look at the direction that the object's moving in. So my object is moving up the slope. My net force is down the slope. Opposite direction. Okay? Direction's that way. Net force is in the opposite direction. That means theta is 180. Okay? I'm not going to put the 0 in again because we know it's there. That's 5. My v was 2.5. Ooh, no, maybe I should write it so you can read it. It's just one of those things. 2.5 squared. Okay? From here, it is completely a choice thing as to how you solve this. Okay? Personally, I don't like having multiplication and multiplying in brackets and that sort of thing. That's a me thing. Okay? So what I'm going to do is I'm going to take this 118 and 1, 2 and put it on that side already. Okay? So watch what I'm going to do. This is 10, 18 plus my friction is going to be equal to a half, because that's my half, times a 5 times 2.5 squared, all divided by 1, 2 cos 180. Okay? the reason why I do this is it gets rid of a lot of the decimal issues and all sorts of things when you multiply in, and it just makes life easier. Okay, so what we're going to need to do is we're going to need to calculate it. So I'm going to put this on this side, okay, and we'll do the function I learned in the last session because I was watching. Okay, so we've got 0.5, and I'm sure most of you know how to use your fraction button, which is actually great, times 5 times 2.5 squared, okay, and that's divided by 1.2 times cos 180, and no, I did something wrong, so I wasn't paying all my attention. What did that do? Didn't like that. Okay, there we go, let's go, equals, no, I wasn't paying enough attention, I'm just going to do it the way I know how to do it. How does that sound? 2.5 times 5, times 5 times 2.5 squared. That's why you got to pay attention. Oops. Divided by, no. Okay, the way I like to do is then I put an equal sign, so I've got an answer. Now I take that answer and I'm going to divide by 1.2 times cos 180 equals, okay, fraction. We don't like fractions. Take the fraction away. And I should have put a negative in there, so actually this is a positive answer, and we get 13, oops, would help if I remember, 13,02, okay? So 10,18 plus my friction equals 13,02, okay? Now, we go, okay, cool, not a problem. So we get 10,18. So much easier to not do this, because now all I do is take the 10,18 over. Okay, so this is actually 13,02. So I'm going to go 13.02 minus 10.18. And we don't use the fraction, so I love this SD button. Love it. Okay, 2,84. So my friction, 2,84 newtons. Okay, tiny. It's not going to be very big because the parallel force due to gravity is much, much bigger. Okay? Guys, don't get freaked out by questions like this, especially when they start saying, oh, net things. The point here is that if I'm looking at net work, which I know I can calculate, then I need to look at net force. And then that goes back to stuff you did in grade 11 when you did Newton's laws. Okay, and you did force diagrams and free body diagrams and all those sort of things. So don't get too freaked out about it, okay? Just do it step by step. And if you need to do these calculations separately and then bring it all together at the end, that is also okay. You don't have to put it all in one equation, okay? You'll still get all the same marks as long as your marker knows what you've done. Okay, so that's really, really important. Now, I know I actually did that quite quickly, but I'm hoping it's stuck somewhere. Okay, and these questions, practice, 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 practice. Get hold of the past papers. They are wonderful in the past papers. Some of them are mean in the past papers. So get hold of them, okay? So that brings us to power. Yay, we like power. Okay, a motor car. Yay, we like those. With a mass of 800 kilograms, so let's write that down, accelerates from rest, so VI equals 25, no, from rest, VI 0. I'm not sure why I'm doing this, because apparently I'm not doing so well today with writing all the right things down.
What's on your mind?
I don't know.
Okay.
My Easter bunny.
I'm concerned now.
I need chocolate. Moving on. All right, moving on. Moving on. Okay, 0. These to entertain the children. There we go. Final velocity is 25 meters per second. And it does this in a time of 20 seconds. Okay, what is the motor car's power? Okay, so let's start at the beginning and we say, well, power, basic equation is work divided by time. work generally would be F delta X cos theta. I don't know force, and I don't know distance. So we've got to go to another one, which says to us that net work is changing kinetic energy. Now, to work out changing kinetic energy, I need to know mass, which I have, and I need to know velocities, which I have. Yay! So what we're going to do is, instead of net work there, okay, so watch what I'm going to do, is I know that net work, which is what I'm going to need to use, is changing kinetic energy, okay, which means I'm going to go final kinetic energy minus initial kinetic energy, okay? Let's do this in 2 steps. You really don't have to do it in one. Okay, so let's first work out work. And that means I'm going to have to go a half mvf squared final minus initial. Now, hopefully, if your maths is really strong, you'll actually notice that a half m is a constant. You can take it out, but let's not do that. Okay, let's just not make it too complicated. So I have a half times 800. My final velocity was 25. My initial was 0, so actually I don't even need to put it in because it's 0. So we'll go to that wonderful thing called the calculator, and we go half times 800 times 25 squared. No, not that one. 25 squared, and we get 250,000, okay? Measured in joules, okay? But that wasn't the question. The question is, what is the power of the motor? So now I know W net, I know time. So we write the equation down again. Guys, please be careful here. What happens in a test or an exam is you get very excited. You write down P equals W over T, and you know you've got to use it. Then you do all this calculation, and then randomly I just see numbers put into an equation and I get an answer. Please don't do that. Write the equation again. Okay, so W net over delta T. So it's 2,500, well, 250,000, divided by time, which was 20. So we go back here, and we're going to go that answer divided by 20, and I get 12,000 and 12,500. It's a good thing I can read as well. 12,500, and power is measured in watts. W, big W. Okay, be careful there. Alrighty. So, yay. Generally, power will be a big number, okay? But it depends on what you're looking at. If we had to work out the power of me walking up a flight of stairs, little number. Take a long time. 80 working up there, big number, take short time. Okay, depends. So just be careful. But generally with motors and stuff, they have to be quite powerful to do the work they're doing. If you had a car that's power was only 100 watts, I'd be worried. Because you ain't going to go very far. Okay, even in a little one. And I got a little car, and it's more powerful than that. Okay. Alrighty. Now, an electric pump is used to bring water out of a borehole that is 40 meters deep. If 1,200 kilograms of water is required every 2 minutes, and the water is let out at 12 meters per second, what must the minimum power of the motor be? So we go, okay, we have 1,200 kilograms of water every 2 minutes, and the water is let out at 12 meters per second. So now we've got to think about this and go, okay, when we look at this and we say, okay, well, 40 meters deep, we know the distance it's got to go, okay, we know we could work this out a couple of ways, okay, but the water is coming out at 12 meters per second. So there's more than one way to work this out, okay? We can go the W net route, okay? So we can go W net equals delta K. sorry, delta EK. Okay, and the change in kinetic energy, it's been laid out at 12, so it starts at 0 and ends up at 12. Okay, so the final is 12 meters per second. It's not going at a constant 12 meters per second to begin with. Okay, so it ends up going at 12. So final minus initial. Okay, and I'm actually going to let you guys work that out, because once I've worked that out, because then I can go power equals W net divided by delta T. The thing about delta T, though, is that it's got to be in seconds, not minutes. Seconds. That means I've got to divide this work by how many seconds? 2 times 60, 120. Okay? So I'm going to leave that for you to see if you can find an answer for it, and then we'll do it in the next section.
Next section. Yeah. All right. While we're going to do that, you're also going to show us that trick, remember?
Yes, I haven't forgotten.
Haven't forgot?
Yes, I'm going to show it at the end of this.
Awesme. So
Yes.
once it is, you've got a lot to do. Let me not waste your time, and keep your questions coming on facebook.com/learnextra. But above it all, let's help one another on the page. I see some of you are paying some attention. So guys, let's keep it like that. Help one another also. See you after the break. Welcome back, Awesome Metrics. Now, just to give you a hint, the metric timetable, final timetable, is out already, and I'll share the link with you guys. So that really shows you really don't have time, but to work and have power. Use the power to work.
Yeah, it just goes from bad from worse. Okay, anyway, moving on. And the physics and chemistry papers are early. They're they're actually quite early. And remember, you'll write them on a Friday and a Monday. So it's crunch time. Okay, I know there's questions.
Yes.
I know. But we've got to go back to something quickly and do the challenge question in 2 seconds.
Cool.
Okay, I promise we'll get to as many questions as we can. All right, now if some of you actually were doing what I told you to do, and you work out this question, you're going to get a power answer here of 720 watts. And hopefully someone is going, hang on, wait, Tracy, seriously? 720 watts? Good. It's wrong. There's not a chance this can be 720 watts. There was nothing wrong with the process of what we were thinking about, okay? But we've got to rethink that reading of the question. The water is let out at 12 meters per second. So that means that the water is moving at a constant velocity of 12, okay? So we're going to go back to the equation of P equals FV, okay? Because if P equals, and this is average power, this would be my minimum, force times velocity, okay? Now we've got to think about what the force is that we have to apply. The force applied to the water is going to be 1,200 kilograms times 9,8. And I'm losing my earpiece. It's been a while. It doesn't like the glasses and the headband. And anyway, so my force becomes 1,200 times the 9,8 times 12. Okay, so now watch. We get 1,200 times 9.8 times 12. That is a much better number, 141,120. Now I'm going to show you my trick, because often you need to put your answers into scientific notation. This isn't so bad, okay, because it's not that complicated. But you know what? Sometimes the numbers get really long and we don't want to use them. So now watch. I love this mode. If you go onto your calculator, so we're going to go here, shift, okay, second function, mode. Now there's a whole bunch of modes here, okay? The one you want to select is number 7, which is scientific notation. And then it gives you a range from 0 to 9. That tells you how many numbers you want in your number, including the one before the 0. Now we need to go to 2 decimal places, so we need the whole number, and then we need 2 decimals. So we put the number 3, and look at that. I have a completely, perfectly rounded off number in scientific notation. So I could write my answer here as being 1,41 times 5 to the 10 to the 5 watts. If of course, we now go, okay, nice in scientific mode, and now we need to go back because now we need to do normal numbers. We go second function mode. We go to number 8, which is normal. We press 2, and voila, we have the answer the way it was. Okay, so second function mode. That changes your to scientific and normal. And also, if you are one of those who forgets to put your things as a decimal and you need to take it off maths display, you press number 2, and now it won't ever give you an answer as a fraction. I like those.
Wow.
And if you go back and you go second function mode and you press number 1 and you say you want maths, so you want 1, it now gives it you back in fractions.
Wow.
So there's moments. I like this calculator, you see? Okay. I know we've got to do questions. Challenge question won't take long. I'm hoping you guys didn't struggle too much. Challenge question. Object X, okay, X gets lifted through a distance of y by a force of F in a time of t. Object Y, even better, it's a little, don't know what it is, gets lifted through X by a force of F in 2e. First of all, the amount of work done on both of these objects is identical. Why? Because work equals Fx cos theta. F is the same for both of them, X is the same for both of them, theta is the same for both. Work is the same, okay? However, X has more power. Why? Because power is work divided by time. It takes longer for Y to do it, okay? So Y takes longer, Y is less powerful than X, but X and Y have exactly the same amount of work. I'm hoping some of them got that. Do we have some of those answers somewhere, that X and Y have the same amount of work?
Let me see the one I have.
Just checking, hopefully.
Checking.
Checking. See, now I put him on the spot.
I'm refreshing. Okay. Let's
Same
see.
amount of work?
Same amount of work.
Work and power?
The amount of work is the same, yes.
Yes,
Rangani
good,
got
well
that
done.
one. And Shintunzugo also got that one. Work done, both will be the same, but power of the object X will be greater than the power of object Y.
Done! Yay!
Can you pronounce his name? Shitunzugo.
Not a chance.
Okay.
Okay, it's not even worth trying to butcher your names. I'm just going to put it out there. It's shame. It's not fair on you. It's not fair on your mummies and daddies
But
who named
his
you.
other name is Ambitious.
Oh, what?
Ambitious. Ambitious.
Ambitious.
Yes.
Anyway, moving on. Okay.
Questions.
Questions.
Yes.
Let's do this.
First one from Tsepo. How do we know which angle to use when work is done on an object?
You must, when you're looking at the angle, Tsepo, is you look at the, okay, let's get to some blank pages. There we go. When you're looking at the angle, look at the direction that the object's going in. Okay, so if you have an object going straight, so going horizontal, look at where the forces are in relation to it and the directions. This was always a good idea to draw a diagram. So for example, an applied force pushes this way, friction pushes that way, okay? So now you go, these are the easiest. Applied force, direction of motion, same direction, theta is naught, okay? Direction's going that way, friction goes backwards, 180, because I'm going 180 degrees around to get to the other direction, okay? You're not often going to work with it at an angle other than 0 or 180, unless, of course, you're now looking at, say, instead of having a force that does this, they say to you, you have an applied force at an angle of 30. Then you would use the 30 degrees. But, of course, by using the 30 degrees, you're working out the component. That's at naught. So it's just a continuation of what you learned in grade 11.
Okay. Bongi and other mindsetters are asking, question B on the second step of the substitution.
Yeah.
Where's the negative sign?
The negative sign. Okay, let's go back to part B. So we're here. No, next, that one. Where's the negative
Question
sign?
B, second step.
Oh, yes, over here. Because I forgot to write it in over there. They are correct. Sorry. That's true. I did forget to write it in. But actually what will happen along the way, which is quite important, is that negative is going to be cancelled out by the cos 180 because cos 180 is negative 1. Okay, so that's why I get a positive answer at the end anyway.
Okay. Right. What is the difference between power and average power? That is from Tabo.
Okay. when they talk average power is when you think about like the motor lifting up the water, okay? When it starts, it's going to have a maximum amount of power. When it ends, its power drops off, okay? And in reality, it goes through ebbs and flows because of also the fact that we use alternating current and we do all sorts of things. So when we're looking at average, we're going, well, if we take the maximum and the minimum, add them together, what do we get as an average, okay? When we're just talking about car motors, and my earpiece is really starting to irritate me in case anyone has noticed. Sorry, it's just me. I'm fine now, sorry. When we're talking about normal power, we're pretty much always talking about average power. We just don't always call it that. Okay, but very specifically, if we're talking about something that's going at constant velocity, we have to deal with average. Okay, when we're dealing with something that is got a net work being applied to it or anything like that, then we're just dealing with power overall. Okay. Yeah.
Okay. Based on question 3, Mpoza says I'm kind of confused there. Is the answer for question 3 720
No.
watts? Or
Yeah. Sorry, I confused you guys there. I'm sorry. It's not 720. It's the 1,41 times 10 to the 4. Okay. The net work using, and it's a little bit of an issue because of the way that your network works, okay? Using network here, it only considers the change in velocity. It's not considering the change in height. And that's a problem. This equation considers the change in height as well. And that is actually very important. Okay, so you've got to consider the change in height as well.
thanks, my sisters, for paying attention.
Yeah.
And Bafana saying that is extremely wrong. So thank you.
What's
for
extremely
noting
wrong?
that.
The 720?
Yes.
How rude. I agree, it is very wrong.
And you know what he even said? I asked,
Yes.
which function do you normally struggle with out of all the 254 functions?
Yes.
He says the one that you didn't mention. That is Bafana for you.
But fine, that's
House head,
rude.
house head, Mahlangu. No wonder why you're house head.
That's
Just kidding.
rude.
Just kidding. Here's
Hey,
another
they sound
question.
like the kids I teach.
Here's another question. Bobo says, why did you use the F parallel instead of the F perpendicular?
Okay, that's for number 3. For number 1, okay. For this one, the reason why, if we look at this, okay, I can't use F perpendicular because theta then ends up being 90 degrees. Cos 90 is 0, okay? And my object on this is moving parallel to the slope. So I really want the forces that are parallel to the motion. Okay, anything going perpendicular to the motion is useless. So your theta cannot be 90. That is one of the criteria. If theta is 90 degrees, your value is 0. So perpendicular makes absolutely no sense, okay, because then you end up with cos 90 and that's 0. So your teacher might have, and there's nothing wrong with this, okay, is sometimes just to be complete, your teacher will look at all the forces acting on the object, okay, which is the normal force, the F perpendicular, but the normal force and the perpendicular gravitational force do absolutely nothing in terms of work because it's 90 degrees, okay.
Okay. Moans says, is it okay to substitute 9.8 as my acceleration if I'm not provided with one, even when an object is not moving vertically?
No. You can only use 9.8 when you're looking at weight, okay? And it will always go into FG that's where you're going to use 9.8. With these questions, they're not going to give you the acceleration when the velocity changes because they expect you to use change in kinetic energy, okay? So the 9.8 is very specific because it's to do with gravity, and gravity is 9.8, so you have to use that, and it will be on your information sheet.
Okay. Luanda, how do we know which angle to use, especially on inclined objects? I think it's similar to the
Very
first
similar.
question.
It's the same thing. Okay, sorry. Anyway, it's the same thing, okay? Pretty much, with a very few exceptions, you're going to use 0 or 180, okay, even on an incline. Because on the incline, I look at the forces that run parallel, which is why I worked out FG parallel in the beginning. Okay, so I go and reduce my forces so that it will only be 0 and 180. So it just makes life so much easier at the end. And then you just literally look at it and go, it's going in the same direction as it's moving. That's 0, going in the opposite direction, 180. Okay.
Kim.
Yeah.
Last one for now.
Oh, wow. Okay.
Where did you go? Sandile says, please show me how to calculate the W net using the formula that you used in the last question. Or please repeat the question for me.
Okay, sweetie, the W net in the last question can't actually be calculated using, when we look at it for question 3, using the equation W net equals delta K is actually a problem, okay? Because you have your F net is where the issue comes in here, okay? In that your F net is going to be your gravitational force, okay? So if we look at this one would have to change. I actually can't use delta EK here, okay? So if you want to go the route of doing W net, okay, you can't use delta K, EK, but you can go, if we use W net, that means I would have to use F net delta X cos theta. Okay, now what we have to recognize is that F net is actually the force of the pump, which would need to be the same force as, and we couldn't use F net, I'm lying to you, this has to be FG. Okay, W net is actually 0 because it's going at a constant speed of 12 meters per second, okay? Going at 12 meters per second means that delta EK isn't actually changing. If delta EK isn't changing, W net is 0, okay? Because force up equals force down can go at constant velocity, which means we would need to work out WG, okay? Work done by gravity, which is the work done by done against gravity, okay? So this is the work done by the pump, and that would then be the 1,200 times 9,8. It's going to go 40 meters, okay? And gravity's in the opposite direction that it's moving in, so this is cos 180. I'm going to have to go quite quickly because I didn't actually work this part out. So 1,200 times 9.8 times 40 times cos 180. So we get minus 4,000, and I'm not getting the right answer for that too. You know what? I think we should just give this up as a bad joke, actually. Why am I not getting the right answer?
Come on now, Tracy.
I'm thinking! Okay, because this takes into account the height that it's going through, and then we would divide this by 1,200. No, 1,200, hello. Even worse. Okay. Well, the only way you can do this is not by working out W net at all, is what I'm trying to say to you, because I know this answer is making no sense. Okay, because, and I've got to do this quickly. Sweetie, I know you wanted W net. You can't work it out for this because it's actually 0, because it's going at constant velocity, up and down equals to 0. You can't use W net. Have to use P equals FB.
Awesome. Thank you so much, Tracy. It's a wrap.
It is a wrap.
For you. For you mindsetters, remember next week we have an awesome revision package just for you guys. We know it's going to be a holiday for most of you, but it is not time to just relax, sleep, eat, and then sleep again. But it is time to, yes, relax, but work at the same time. So we have a revision the whole week. Tune in onto Mindset because we have shows that will help you through it. But for today, we just want to say thank you very much for tuning in. I'm leaving you with an awesome quote from Boy Dumelo saying, a wise man once said, the road of education is bitter, but the fruit of education is sweeter. Thank you so much, Boy Dumelo, Precious Mate, for that. And to us, we just want to say to you guys, it's a wrap and peace. We love you.